Hey everyone, Mr. Fransky here again. We're going to try some more related rates problems, and we're going to learn a little bit different method as well, one that you might have seen on the solutions to this to the sheet. So today, just going to be able to solve related rates problems using the four-step system and the grid. We have the same vocabulary we had before, and the grid system. If you look at on Schoology, there's a set of solutions called Fransky solutions. That one I use kind of the four-step system we talked about in the last video. There's also one that's called Galt solutions. She uses a chart. It looks like this. And it actually lists this on the first problem, but there's a picture. Then there is, I want to make sure I get this right, equation, I believe. And then it's derivative, always implicitly because you have to chain on the t. And then there is solve. And in the middle, you put what you're looking for. So like in that first problem, we're looking for dA dt. You put that in the middle, and that's like the focus of what's happening. And then you draw a picture, then you write the equation, pi r squared. And I believe she also writes the information you know over here. Like we knew that r is equal to something. We also know dr dt. And then derive would be dA dt equals 2 pi r dr dt. And then over here, you actually do the solving by plugging the pieces into the equation. So if you like this kind of an organizational setup, you can. I will always do it with the what we know, what we want, and what we need, and then I'll solve from there. Okay. All right, so let's try some more examples. A rocket is rising straight up from a level platform. At the moment, the angle of elevation for an observer 1,000 feet away is pi over 3 radians. The angle is increasing by 0.5 radians per minute. How fast is the rocket rising at that moment? So let's draw what's going on here. We got our observer. It's 1,000 feet away from a launch pad, and the rocket is going up. Okay. So let's see here. They're 1,000 feet away. The rocket is only going up. So that 1,000 is never changing. So I'm going to put 1,000 there. And they tell us the angle of elevation is something that's important. So I'm going to draw this in. I'm going to put a theta right there. But that's changing, right? And let's put an x over here. Let's call it y, actually, since it's vertical. Okay, so the rocket is rising up. This is definitely changing, so I'm not going to give a number there. And this is also changing because this person is looking up higher and higher and higher as the rocket elevates. So what we know, what do we know here? We know that the angle is increasing by 0.5 radians per minute. So let's call that d theta dt. So the angle is changing with respect to time at 0.5 radians per minute. Okay, and let's see. And they want to know how fast the rocket is rising. So we want dy dt. Looks like we're going to have to use some trig here. So we want dy dt because we want to know how fast the rocket is rising. That'd be the velocity it's rising up. Okay, so what we need is to relate theta and y. Okay, we need to relate theta and y. So we're going to have to find an equation that does that. So it looks like we have theta here in the corner. We have the opposite and the adjacent. Is there a trig function we know with SOHCAHTOA that will use the opposite and adjacent? Like that's tangent. So tan theta is equal to y over 1,000. So now we take the derivative of both sides with respect to time. So derivative of tangent is secant squared theta. Now we chain, so times d theta dt. And that'll be equal to the derivative over here. I'm just going to change that to a 1 over 1,000. And the derivative of y is just dy dt. And that's what I'm looking for, right? I'm looking for dy dt. I know everything else. So at this moment, they tell us that theta is pi over 3 radians. So I'm going to do secant squared of pi over 3 times d theta dt, which is 0.5. And then let's multiply that by 1,000 right now. And that's going to be equal to dy dt. That's what I'm looking for. Secant of pi over 3, that's 1 over cosine squared of pi over 3. Cosine of pi over 3, unit circle, that's right there. Cosine is the short value, that's 1/2. So this is 1 over 1/2 squared. That's 1 over a fourth, which is 4. So I have 4 times 0.5 times 1,000 is equal to dy dt. Half of 4 is 2 times 1,000 is 2,000. So we have 2,000 is equal to dy dt. And the units on this, let's see, they're talking about 1,000 feet away, so that's going to be feet per minute. So it's 2,000 feet per minute. There you go. It's pretty fast. Okay. All right. A 13-foot ladder is leaning against the house. I've been talking about ladder problems for a while. Finally, we get one. So here's our 13-foot ladder leaning against the house. When its base starts to slide away from the house. By the time the base of the ladder is 12 feet from the house, the base is moving at a rate of 5 feet per second. How fast is the top of the ladder sliding down the wall? All right, so we need some letters. So it tells us that a 13-foot ladder, so that's 13. That does not change, right? The X and the Y here I'm going to put in because those are changing. Now, what do they give us? What do we know? Well, we know that the base is sliding away from the house at a rate of 5 feet per second. That's dx dt. X is growing, right? X is increasing because the distance here is increasing. So dx dt is a positive 5 feet per second. What I want is dy dt. And dy dt, is that going to be a positive or a negative value? I think it's going to be negative because it's decreasing, right? Y is getting smaller. Okay, so what I need is to relate x and y, right? Because I know dx dt, I want dy dt, I have to relate x and y. Well, this is a right triangle, so I have x squared plus y squared equals 13 squared, which is 169. Okay, so now we derive with respect to time, so 2x times dx dt plus 2y times dy dt is equal to, what's the derivative of 169? I think it's 0, right? It's a constant. It's a flat line, no slope. Okay, so now let's see what we know. We know the base of the ladder is 12 feet from the house, so x is 12. So I have 2, and actually, this is a little trick. I can just get rid of all the 2's, right? Let's just divide both sides by 2. So I have x dx dt plus y dy dt is equal to 0. Okay, so now we plug in what we know. We know x is 12, so I have 12 dx dt, and dx dt is 5, we know that. So 12 times 5 plus y dy dt equals 0. Now you might think, uh-oh, we have two variables, right? We don't know y and we don't know dy dt. But we know at this moment, x is 12, and this is 13. I can find what y is at that moment. And it's okay to do this now because at this moment, I can know what the y value is by using Pythagorean theorem. So I have y squared plus 12 squared equals 13 squared. So that's y squared plus 144 equals 169. 169 minus 144 is 25, so y squared is 25. So y is 5 at that moment. So we put in a 5 here. So we have 60 plus 5 dy dt equals 0. Subtract 60 and divide by 5. Dy dt is negative 60 over 5, which is negative 12. So it's negative as we suspected, right? So negative 12, and that's going to be feet per second. Nice. Okay. I think I got one more. Ah, yes, the conical question. So water is poured into a conical cup. Here's our cone. Okay, so it's like one of those little paper cups at a rate of 2/3 cubic inches per second. So we got water going in here at a constant volume rate. If the cup is 6 inches tall and the top of the cup has a radius of 2 inches, how fast is the water level rising when the water is 4 inches deep? And they give us the volume of a cone right there. So here's our cone. They tell us the radius of the cone, and that never changes. The radius of the cup has 2 inches. And they tell us the height of the cup is 6. Okay? We want to know how fast the water level is rising when the water is 4 inches deep. So the water is 4 inches deep, right? And we want to know how fast the level is rising. So what the height is changing. So we know the volume, the change in volume, right? dV dt, right here they tell us is 2/3 cubic inches per second. Okay? What we want to know how the height is changing, right? So h at any given moment. So we want dh dt. So we need an equation that involves only v and h. We need to relate v and h. So we can almost do that because we have an equation for the volume right here. V is 1/3 pi r squared h. Now there's a problem there, right? We have an r and an h in this equation. We need it to just have a v and an h. Because if I start doing this, I could use product rule here. It gets kind of messy. But then I have to figure out how r and h are related, and I don't know that, right? So what I'm going to do is I'm going to set up a series of similar triangles here. Every time you have a cone problem, you're going to have similar triangles. So let's break those triangles out. So the big triangle has a height of 6, and this top radius is 2. At any moment, h and r are going to have that same ratio. So every time you have a cone problem, you're going to do this. So you have h and r. So I'm going to set up a ratio. What I'm going to do is I'm going to do 6 to 2 is equal to h to r. And again, you can set this up a couple different ways. You can do 6 to h is 2 to r. You can do r to 2 is h to 6. You can do 2 to 6 is r to h, as long as you use the same direction for both of them. I like this because now I get a whole number. So I have 3 equals h over r. Or I can also write that as h equals 3r. Or I could write r equals h over 3. Now let's choose which one of these we want to use. I want an equation that has only v and h in it. So I want to get rid of the r. I think I want to use this one, right? Because now it'll only have h's and v's. So v is equal to 1/3 pi times radius is h over 3 squared times h. All right. So that is v is equal to 1/3 pi times h squared over 9 times h. So let's write that one more way, just to make it a little cleaner. So that's 1/27. Let's write pi over 27. That's our constant out in the front, times h cubed. That's a nice clean equation. So now we derive with respect to time. dv dt is equal to pi over 27 is a constant, times 3h squared times dh dt. And now is when I'm going to look at what's actually going on at this moment. So at this moment, they tell us that the water is 4 inches deep. So now I'm going to be able to plug that in for my height. So at the moment that it's 4 inches deep, the volume dv dt is always the same. So I have 2/3 for dv dt, and pi over 27 is my constant out front. And that's going to be times 3 times my height at this moment is 4, so 4 squared. And then dh dt is what I'm looking for. And that's the only variable I have left. It's the only thing I'm looking for. So let's see here. I have 2/3 equal to 4 squared. It's like 3/27 is 1/9. So I have pi over 9 times 4 squared, which is 16. And then times dh dt. So I think we can get dh dt by itself in one step here. I have 16 pi over 9, so I'm going to multiply both sides by 9 over 16 pi. So 9 over 16 pi, that gets rid of everything over here, times 2/3 equal to dh dt. 9 over 3 is 3, so it's going to be a 3 on the top. 2 over 16 leaves me with an 8 on the bottom. So I have 3 over 8 pi. Is my dh dt, and let's see if we can get units here. So h is linear, it changes in inches, feet, miles, whatever that is. So this is going to be inches per second. That's dh dt. All right, looks like my slide showed it, but there we go. Okay, so 3 over 8 pi inches cubed per second, or inches per second. So tricky problem. The cone ones always seem to throw people for a loop. It's important that you can do the similar triangles, that you can get it in terms of just the two variables that you want, and then that you can solve it out by deriving both sides with respect to time. I love you guys. That's why I'm here. Have a great day.